Example 6. Find the maclaurin series for the function f of x equals x cosine of x. Solution. Instead of computing derivatives and substituting in equation 7, it's easier to multiply the series for cosine of x, equation 16, by x. X times cosine of x equals x times the sum from n equals 0 to infinity of open -1 close to the power n times x to the power 2n over open 2n close factorial equals the sum from n equals 0 to infinity of open -1 close to the power n times x to the power 2n plus 1 over open 2n close factorial. Example 7. Represent f of x equals sine of x as the sum of its Taylor series centered at pi over 3. Solution. Arranging our work in columns, we have f of x equals sine of x, f open pi over 3 close equals the square root of 3 over 2. F prime of x, or the first derivative of f at x, equals cosine x. The first derivative of f of pi over 3 is equal to 1/2. The second derivative of f of x equals negative sine x. The second derivative of f of pi over 3 is equal to negative the square root of 3 over 2. And the f triple prime, or the third derivative of f of x, equals negative cosine x, where the f triple prime of pi over 3 equals negative 1/2. And this pattern repeats indefinitely. Therefore, the Taylor series at pi over 3 is f of pi over 3 plus the first derivative of f of pi over 3 over 1 factorial times open x minus pi over 3 close plus the second derivative of f of pi over 3 over 2 factorial times open x minus pi over 3 close squared plus the third derivative of f of pi over 3 over 3 factorial times open x minus pi over 3 close to the power 3 plus ellipsis equals the square root of 3 over 2 plus 1 over 2 times 1 factorial times open x minus pi over 3 close minus the square root of 3 over 2 times 2 factorial times open x minus pi over 3 close to the power 2 minus 1 over 2 times 3 factorial times open x minus pi over 3 close to the power 3 plus ellipsis. The proof that this series represents sine for all x is very similar to that in example 4. Just replace x by x minus pi over 3 in equation 14. We can write the series in sigma notation if we separate the terms that contain the square root of 3. Sine x equals the sum from n equals 0 to infinity of open -1 closed to the power n times the square root of 3 over 2 open to n closed factorial times open x minus pi over 3 closed to the power 2n plus the sum from n equals 0 to infinity of open -1 closed to the power n over 2 open to n plus 1 closed factorial times open x minus pi over 3 closed to the power 2n plus 1. Sidebar, we have obtained two different series representations for sine x. The maclaurin series in example 4 and the Taylor series in example 7. It is best to use the maclaurin series for values of x near 0 and the Taylor series for x near pi over 3. Notice that the third Taylor polynomial, big T sub 3, in figure 3 is a good approximation to sine x near pi over 3, but not as good near 0. Compare it with the third maclaurin polynomial, big T sub 3, in figure 2, where the opposite is true. Figure 3, y equals sine x, and you have t, big T sub 3, and on the x-axis you have pi over 3. Returning to the text, the power series that we obtained by indirect methods in example 5 and 6 in section 11.9 are indeed the Taylor or maclaurin series of the given functions, because theorem 5 asserts that no matter how a power series representation f of x equals the sum of c sub n of f of x equals the sum of c sub n open x minus a closed to the power n is obtained, it is always true that c sub n equals the nth derivative of f of a over n factorial. In other words, the coefficients are uniquely determined.